Good afternoon, students. So, good afternoon, students. Good afternoon, JNV Raichu. So, am I visible and audible to you guys? So then let me know in the chat box if I'm visible to you all. JNV Raichu. So, can you able to see my screen and is my voice audible? Yes. Okay. So, a very good afternoon to you guys once again, and moving on to the today's session. So, we have been discussing about the solutions list. Right. So in the last class, we have discussed some problems, numericals related to the topics which we have discussed in the previous classes. That is from classification from Henry's law, etc. Right, and from concentration terms. So today, before moving on to the new topic, I would just want to give a recall test for you guys. Okay, I have given in the last class. Now tell me, what is molarity? What is the formula for molarity? Can you give me the formula for molarity? So using this formula, we have solved many problems in yesterday's class, in last class, and on the day which we have discussed this topic, right? So what is the formula we have used for molarity? Number of moles per volume of solution. Very good. It is number of moles per volume of solution. Okay. Then coming to the next question. Define Henry's law. Define Henry's law. What is Henry's law? Or give me the formula for Henry's law. What is the formula which we have been used for Henry's law? Very easy, no? Partial pressure is directly proportional to, yeah, no, partial pressure. It is not vapor pressure. It is partial pressure, which is proportional to mole fraction. Very good. And we have used a constant called Henry's constant over there, which is denoted by Kh, and it is inversely proportional to solubility, and many more informations were discussed in that. Okay. Now moving on to today's session. So today we are going to learn about the vapor pressure and Raoult's law. Okay. So now I'm going to give you a picture. Okay. So have you ever observed this? Evaporation of a liquid in an open vessel, liquid molecules escaping into atmosphere. So now the container is open here and we have a solvent and it is producing some vapors. So what will happen if we keep this liquid in an open container? What will happen? Evaporation is happening. So when a liquid in an open glass vessel is left open without covering with a lid, after some time, the level of the liquid in vessel is found to decrease. So why the level of the liquid in vessel is decreasing? Because due to evaporation. And we call this process as evaporation. Okay. Suppose instead of keeping the container open, if I keep the container in a closed form, what will happen? Now the vessel is covered with a lid. liquid droplets are condensing on the walls and are getting falling back, right? If the liquid is placed in a closed glass vessel after some time, it is observed that droplets of liquid can be collected on the walls of the container. And we call this process as condensation. Okay. So evaporation means the volume will decrease. And if the droplets are coming back to the system, then we call that as condensation. Now, the pressure exerted by the vapor over the liquid surface where there exists an equilibrium between the vapor and the liquid at a particular temperature is called as vapor pressure. So we have a container, okay, and there are some liquid molecules and they are also producing some vapors. Okay. Now the pressure will be exerted by this vapor on the liquid surface of this liquid. And at this point, there will exist an equilibrium. There will be an equilibrium existing between the vapor and the liquid molecules. Okay, so that we call as vapor pressure. Okay, we call that as vapor pressure. And different liquids have different vapor pressure at the same temperature. Okay, suppose water may have some other vapor pressure value. And if I take benzene, that will have different vapor pressure value. Okay, the temperature will be same, but the vapor pressures will be different for each liquid. Okay, so do you know the reason behind this? So like why different liquids are having different vapor pressure? Any idea? Do any of you have any idea about this? Yes or no? So why do different liquids have different vapor pressure? So it is because of the attractive forces between molecules are different depending upon the nature of the liquid. Okay. So suppose if I take a water molecule, so this is one water molecule and this is the other water molecule. Okay. So there will be an attractive force which will be existing between these two water molecules. And if I take benzene or some other solvents, so the attraction between those two molecules will be different. Okay. So if the attractive forces are different, then the vapor pressure will also be different. Some may get boiled easily and some will take some time. So boiling point will be differing for two liquids. So in that case, the vapor pressure will also be different. Got it? Is this clear? So coming to the next point, the vapor pressure of liquid solution. So the concept we are going to learn in today's session is vapor pressure of liquid solution. So far I have been explaining you the meaning for vapor pressure. Okay. Now let's see that vapor pressure of liquid solution. Now we do have liquid solutions which are formed when solvent is a liquid. Okay, when solvent is a liquid, we call that as liquid solution. We have seen, no, in the previous sessions, we have discussed about some 9 types of solution. And in that, if the solute is a liquid and solvent is also a liquid, then that is called as liquid solution. Okay, not only in that case, if solvent is a liquid, solute may be anything. If solvent is a liquid, we call those solutions as liquid solution. Okay, it can be gas in solid or solid in, gas in liquid or solid in liquid or liquid in liquid. So all these three combinations are called as liquid solutions. Okay, solute can be a solid, gas or liquid. Now the solution containing two components are called as binary solutions. These things we have discussed in the first class itself. Okay, so the two components, if the two components are liquid, then we call that binary solution as liquid and liquid solution. If the two components are solid and the other one is, if it is liquid, then we call that as solid and liquid solution. So we are going to discuss in detail about these two. Okay. So first let me go with the vapor pressure of liquid in liquid solution. Okay. The vapor pressure of liquid in liquid solution. So it is nothing but a binary solution containing two volatile liquids. Okay. So these are the two components. These are the components 1 and 2 taken in a closed vessel. So let me show you the picture here. So this is the picture and the top part is the vapor phase part and the bottom we have a liquid phase. Okay. So now what is going to happen? Both the components vaporize and the equilibrium state is attained or it is established between the vapor phase and the liquid phase. Okay. So we have two components here in the liquid phase. Okay. So we have the vapor phase and we have a liquid phase. So there will be an equilibrium existing between these two. Okay. Because of the vaporization process. And in a binary solution of two liquids, if you take, let P1 be the partial vapor pressure of the first component and P2 be the partial vapor pressure of the second component. So what is meant by partial pressure first of all? So we have two components. One is component 1 and the other one is component 2. Okay. So the pressure for this component is P1 and pressure for this component is P2. Okay. Now if I add these two, so what I will get? I will get a solution. Okay. I will get a solution. This is a solution in which we have both the component 1 and 2 and the solution will have some vapor pressure that is called as total vapor pressure. Okay. So this solution contains the component of 1 as well as the component of 2. Now, if I have to find out the vapor pressure of only the component 1 from the solution, then I call that as partial vapor pressure. And I call that as partial vapor pressure, the part of the first component which is present inside the solution. Clear for all of you? Then coming to P2, it is the component number 2. So P2 is the partial vapor pressure of the second component. And P total be the total vapor pressure of the solution. So is this clear to all of you guys? This part is very, very important. Okay. So you should know what is meant by partial vapor pressure and you should know what is meant by total vapor pressure. Don't get confused. Instead of writing P1 here, I will write P1 naught and I can write P2 naught here. So this naught denotes the 0 in the superscript denotes the vapor pressure of that particular component in its pure state. Okay, in its pure state. So here I can write P1 and for finding out the partial pressure of the second component, we can take this as P2. So now it is clear, I think. So any doubt from this? Shall I move on to the next slide, students? Now you all will be able to differentiate what is partial pressure and what is total pressure, right? Shall I go with the next slide? If you want to write anything or if you want me to explain any concept again, you can let me know in the chat box. Yeah, okay, students. Now, the total vapor pressure, which is denoted as P total, it becomes equal to the sum of the partial pressure of two components. That is what we have discussed in the previous slide, right? So the component 1 plus component 2 will give the total vapor pressure. So mathematically, it is denoted as P total, which is equal to P1 plus P2. Okay, P1 plus P2, which is very important formula. Now there is a note for you. The partial pressures are related to mole fractions of the two components respectively. So in case of Henry's law also, we have seen that same thing only. Partial pressure was related to mole fraction, but the component was a gas. Henry's law is for gases. Okay. Here also it is partial pressure is related to mole fraction only, but this is a case with liquid. Okay, this is a case with liquid. So before moving on to the next topic, I would like to go with one multiple choice question for you. So let's solve this and then we'll go for the next thing. So if P1, P2 and P3 are the partial pressures, then what is P total? Very easy question. So option A is the correct answer, right? So P total is equal to the sum of the partial pressure value. Coming to the next topic, Raoult's law. So this is very important. Raoult's law is very, very important. Okay. So what is Raoult's law? So this law was proposed by the Francois Marc Raoult in 1886. He gave the quantitative relationship between partial pressure and mole fraction. Okay. So this law is very important. We'll state this law now. Okay, we'll state this law. So it states, Raoult's law states that the partial vapor pressure of each component in the solution of volatile liquid is directly proportional to the mole fraction of it in the solution. The same thing. Partial pressure is directly proportional to mole fraction, but it is for volatile liquids, not for gases. Is that okay? So this law is very important. Take a note of it. Now, therefore, we can write P1 partial pressure directly proportional to X1, and for P2 it will be proportional to X2. Okay, partial pressure of two components are directly related to their mole fraction. Where X1 and X2 are the mole fraction of component 1 and 2 respectively. Okay, now therefore P1 is equal to P1 naught into X1 and P2, yeah, this is for component 1, and P2 is equal to P2 naught into X2, and this is for component 2. So from where does this P1 naught and P2 naught have come from? They are the proportionality constant. Okay, here we are having a proportionality symbol now. So if we remove that proportionality symbol, we are introducing a constant here. And in case of Henry's law, we have used KH. Now for Raoult's law, we are using P1 naught and P2. P1 naught is Darcy Baran, want to ask anything? Your mic is unmute. Okay. Okay, thank you. I think by mistake she have. Good. So what is P1 naught and P2 naught? Just before few minutes I was discussing about this P1 naught and P2 naught with you now. So can anyone tell me what it is now? What does P1 naught denotes? What is P1 naught and P2 naught, students? I hope you are all listening. What it is? So they are the vapor pressures of pure component. They are the vapor pressure of pure component. I told you, right? So there is component 1 and 2, and the vapor pressure of that first component is P1 naught, and the vapor pressure of the second component is P2 naught. So P1 naught and P2 naught denotes the vapor pressure of pure components. Okay, don't forget that. So this is for pure component, and this is the partial pressure. That is the partial vapor pressure. So these formulas are very important. They are in accordance with Raoult's law. Now, one more scientist called Dalton. So according to Dalton's law of partial pressure, the total pressure over the solution phase in a container will be the sum of the partial pressure of the component of the solution. Okay, the total pressure is calculated using sum of the partial pressure. So therefore, the final relation will become like P total is equal to P1 plus P2. Okay, this is in accordance with Dalton's law. Now we know that P1 is equal to P1 naught into X1 and P2 is equal to P2 naught into X2. So what you do, substitute those two values in place of P1 and P2 in Dalton's law. Okay, P1 naught into X1 plus P2 naught into X2. Okay, and we already know that sum of the mole fraction X1 plus X2, it will be equal to 1, right? Sum of the mole fraction X1 plus X2 should be equal to 1. So in place of X1, what we can substitute? 1 minus X2. So in place of X1 here in this formula, you can substitute 1 minus X2. Okay, into P1 naught plus P2 naught into X2. The remaining things are written as such. Got it? Now what will happen? You can multiply this. You can multiply this. You can get P1 naught minus 1 into P1 naught is P1 naught. Okay. X2 into P1 naught is minus X2 into P1 naught. So that part is here. And the next part, P2 naught into X2 is written as such. Okay. Now in the next step, what we are going to take? P total is equal to P1 naught plus X2 into P2 naught minus P1 naught. So we are taking this mole fraction of the second component outside. So if we take X2 as common, then it will be P2 naught minus P1 naught. So we are getting a relation like this. So in this page, two formulas are very important. First formula is this. So you'll be using this formula to solve many numericals from Raoult's law. Very important formula. Okay, and the second is last formula. This is like y is equal to mx plus c, right? It is in of this formula. And this is an equation of straight line. Okay, so that part is very important. And these two formulas are important. Just take a note of it. Now, from the above equations, the following conclusion can be drawn. So, what are the conclusions? So, have you all noted down the formula, or you want me to show the previous slide? Shall I proceed, or you want me to show the previous slide, students? Shall I proceed? Have you all taken down the formulas which I have said in the previous slide? Yes or no? Are you all aware? Am I audible? Am I audible or not? Yes. Okay. So I'll proceed. So from the above equations, from the above Raoult's law equations, the first conclusion that we are drawing is the total vapor pressure over the solution can be related to the mole fraction of any component. The total vapor pressure can be, because in that formula, in P total formula, we have P1 naught into X1 plus P2 naught into X2. So where X1 and X2 are the mole fraction, the total vapor pressure is directly related to the mole fraction. So that is the conclusion 1 from the given equation. And then conclusion number 2 is the total vapor pressure over the solution varies linearly. So I told you that we are getting y is equal to mx plus c format kind of equation, which is an equation for straight line. This is an equation for straight line. Okay. Straight line means we get a linear relationship with the mole fraction. The vapor pressure is linearly related with the mole fraction. Okay. So let me give you one graph. So here is the graph, and this graph is very important. Okay. So y-axis is of vapor pressure and x-axis are from mole fraction. Okay. Now when you come to this point, we have x1 and x2, but x1 is 1 and x2 is 0. What is the meaning of this? So the mole fraction of 2 is 0, but only the mole fraction of 1 is given. Means only the pure, what to say, pure component of 1 is present in this point, which is nothing but P1 naught. Okay. Then when you come to this point, we don't have x1 component, we have only the component number 2. Means this line, this point, this line denotes the pure component number 2. P2 naught is only present there. Now, if I connect these two, I am getting P2, and if I connect this point and that point, I am getting P1. So, we know how to write P1 and P2, right? Now, when P1 naught and P2 naught line points are connected with the line, we are getting a P total. Okay, where x1 and x2 are the, actually, x1 is the mole fraction of solvent and x2 is the mole fraction of the solute. Because in two component, one will be in binary solution, one is a solvent and another one is a solute, right? So always one denotes the solvent and two denotes the solute in the upcoming topics also. Okay. So just have a note of it. Now this graphical representation of the vapor pressure versus mole fraction of an ideal solution at constant temperature. This graph is only for ideal solution. In ideal solution, what does it mean by ideal solution? The attractive forces will be zero in case of ideal solution. and the change in enthalpy, those things will be zero, change in volume will be zero, everything will be zero. So there is no attraction between component 1 and component 2. So those solutions are called as ideal solution, and this graph is meant only for that particular system. Okay. Now moving on to the next graph. So we have vapor pressure again, okay, with the same total pressure. Now here you can see some dotted lines. So the dotted lines are denoted by 1 and 2. Okay. So those lines denotes the partial pressure of the component. And the third line denotes the vapor pressure, total vapor pressure of the components. Okay. So each and everything is very important here. And a very important point that you have to note down is the composition of the vapor pressure in equilibrium with the solution is determined by partial pressure, and if Y1 and Y2 are the mole fractions of component 1 and 2 respectively in the vapor phase, so far we have been discussing about the solution. Now we are coming to the vapor phase. If Y1 and Y2 are the mole fractions of component 1 and 2 in vapor phase, then using Dalton's law, P1 is equal to Y1 into P total, P2 is equal to Y2 into P total. Okay, so where Y1 and Y2 are the mole fractions in vapor phase. If I write X1 and X2, this will be the mole fraction in case of liquid phase, and this is in case of vapor phase. Okay, so just take a note of these formulas also. Now Raoult's law, a special case of Henry's law. So how to relate this? Both of them are related with the partial pressure and mole fraction only, right? So the partial pressure of volatile component or a gas is directly proportional to mole fraction in solution. This is a Raoult's law, special case of Henry's law. So where P is directly proportional to X and P is equal to KH into X. This is from Henry. Okay. Now it's the same. Yeah, P is the partial pressure of the gas here and X is the mole fraction of the solution and KH is the Henry's law constant. Okay. So here KH becomes equal to P1 naught in case of Raoult. So instead of this KH, what we are writing in Raoult's law? We are writing P1 naught. So KH becomes equal to P1 naught, or generally we can write this as Pi naught. Okay. So using these relations, we are going to solve some questions from this topic. Okay. So here is a question to you. So before moving on to this question, I would like to ask you a question. So do you have any doubts from the topic, Raoult's law that we have discussed now? So two formulas are very important. Okay. Two formulas which I have given you in one slide, that is very important. And Raoult's law is for liquid, Henry is for gases, and KH is equal to P1 naught here. And the meaning for P1 naught, P1, P2 naught, P2, so those things are very important. Okay. And for vapor phase, mole fraction is written in terms of Y1 and Y2, and that relation is coming from Dalton's. So these are the points you have to take out from this Raoult's law and vapor pressure topic. Okay. So now with this concept, we will go with the question. Vapor pressure of chloroform CHCl3 and dichloromethane are at 298 Kelvin are given as 200 mm of mercury and 415 mm of mercury respectively. Calculate the vapor pressure of the solution prepared by mixing 25.5 gram of chloroform and 40 gram of dichloromethane at 298 Kelvin. So separate vapor pressures are given. We have to find out the solution vapor pressure for the given amount. Now how to approach this question? So first of all, take the molar mass of CHCl3. So how to take down the molar mass of CHCl3? Any idea? So for carbon, the atomic mass is 12, and for hydrogen, the atomic mass is 1, and for chlorine, it is 35.5. Okay, and we have 3 chlorine, so multiply by the number 3. Okay, so we will get 46.5 plus 1 plus 12. So if I add these to what I will get? Oh, sorry. 35.5 into 3 is what? Has anyone got the answer? 35.5 into 3 plus 13. That's 911, right? 119.5. It is not 106, my dear. It is 119.5. 119.5 gram is the molar mass of CHCl3. And what about the molar mass of CH2Cl? Find out fast, and one of you give me the answer. All of you can try and give me the answer. So we have one carbon, 12, two hydrogen, and we have only two chlorine. So 35.5 into 2. One of you have got the answer, I think. 84. Is it 84? What about others? 85, right? Yeah. So 2, 5 is 10, 11, 7. So 71. So 5, 85. So the answer is, yeah, 85 gram is the molar mass of CH2Cl. Now using this molar mass, I am going to find out the number of moles. So why I am doing all this? If we want to find out the vapor pressure of the solution, we need the mole fraction. So mole fraction is nothing but number of moles of that particular component divided by total number of moles. So to find out the number of moles, we need mass and molar mass. So mass is given in the question. Molar mass is not given in the question. So that's why I am getting the molar mass first, and using this value, we are putting the taking the number of moles of CHCl3. So it is equal to weight or mass divided by the molar mass of CHCl3, which is equal to, what is the weight of CHCl3 given in the question? So the weight is 25.5 gram divided by the molar mass of CHCl3 is 119.5. Has anyone got the answer for this? Number of moles of CHCl3. Try to get the answer. At least give me 2 digit after the decimal. 2 digit after the decimal. 3 is needed, but if you have completed with 2, you can put it in the chat box. Very good, very good. So it is 0.213. Good. Yeah, very good, Bharani. Very good. Now coming to the number of moles of CH2Cl. Has anyone got the value? The weight of the CH2Cl2 is 40 gram divided by 85. What is 40 divided by 85? 0.47. Okay, very good. 0.47 is the answer. So we have got the number of moles value for both the components. Now therefore, total number of moles is equal to, add these two, and if you add these two, you will get 0.683 moles as the value. Okay, so that we have got the number of moles. Now the next aim is to find out the mole fraction. So the mole fraction of CHCl3 is equal to number of moles of that component divided by total number of moles. Because what is the formula? If I have to find out for HCl, it is equal to Na divided by Na plus Nb, right? So this is the total number of moles which has been calculated, and it is 0.683. Now the number of moles of component A alone is 0.213. Okay, so I am going to divide these two. Has anyone got the answer? 0.213 divided by 0.683 with at least 2 digits after the decimal. All of you try this in your notebook. Don't stay silent and don't sit simply. All of you try out. Only by practice you will get all the things correctly. Okay. For this kind of lesson, for physical chemistry lessons, knowing the concept alone will not work out. Okay. Yeah. Very good. Very good. The multiplication division parts are very important. And if we know the formula and if we are not able to get the answer by doing correct mathematics, multiplication, division means it doesn't remain, no? So be careful and do practice all the things. So 0.312 is the mole fraction of the first component. Now what about the mole fraction of second component? By this time, yeah, 0.688. Then the NM students are really great. 0.47 divided by 0.683. 683. So it is 0.688. 0.688. Now, using the equation which we have discussed, that is P total is equal to P1 naught plus P2 naught minus P1 naught into X2. P total is equal to, substitute all the values here. So this 200 and 415, who are they? Vapor pressure of the pure component. So if CHCl3 is taken as component number 1, this is P1 naught and 415 is P2 naught. Okay, and we have X1 and X2 also. Just now we have calculated. So apply that, the 200 plus 415 minus 200 into 0.688. Just now we have calculated this now. So substitute everything. And 415 minus 200 into 0.688 will be 147.9. And if we add these two, we will get 347.9 mm of mercury as the value for this question. Okay. So we have got the vapor pressure of the solution. So is this question clear to all of you guys? We are applying this formula. This is the main formula for this question. And to find out the total pressure, we have P1 naught, P2 naught, and P1 naught in the question. We need X2, which is nothing but the mole fraction of the component number 2. So to find out the mole fraction, we are getting, to find out X2, we need N2 and N1. So to find out the number of moles, we have used mass by molar mass formula. Okay. Mass is given in the question and molar mass we have got it. So that's all. Simple. Any doubt from this question? Shall we move on to the next? Yes. Good. Now the next topic is the vapor pressure of solution of solid and liquid. So I have already told that we have two cases here. One is liquid and liquid. So we have completed that. Now we are moving on to solid and liquid. Vapor pressure of the solutions of solids in liquids. Okay. The pressure, what is vapor pressure? Again, coming to the definition of vapor pressure here, the pressure exerted by the vapor molecule of a liquid when they are in equilibrium with the liquid of a given temperature is called vapor pressure of the liquid at that particular temperature. So it differs with the temperature. So that's why we are mentioning that temperature over there. Okay. Now the vapor pressure of the solution is always less than that of the pure solvent. So initially we may have a solvent component and there will be some vapor pressure which is called as P1 naught if this component is taken as one. And also we may have a solute, okay, as component 2. And they will give us the solution. So the vapor pressure of the solution is denoted as P solution or P total, anything. So what the statement says, the vapor pressure of the solution is always less than the vapor pressure of the pure solvent. Okay, so that is the fact. Why? In solution, some of the non-volatile solute molecules from the second component occupies the surface of the solution. So some of the mostly solute particles are solids. Okay, solute particles are solids. So they may go and occupy the surface of the solution. So in that case, what happens? The fraction of the surface covered by the solvent molecules gets reduced. So initially, let me draw once again. So initially, this is the surface of the solvent molecule in which all the solvent molecules are present here. Now in the solution, some of the sites are occupied by solute particle. Okay, like if solid particles are occupying like this, then the fraction of the surface covered by the solvent molecule, what is happening? It is getting reduced. So in that case, only very few solvent molecules can go out. So the vapor pressure will decrease. The vapor pressure in case of solution is always less than that of the pure solvent. Okay. Now here, the vapor pressure of the solution is always less than that of pure liquid. So you can see that in the pictorial form here. This is for pure solvent, the same thing which I have shown you. Now the solid particles are occupying the surfaces here. Now here more number of particles are coming out, but here only very less number of particles are coming out in case of solution. Okay. Now there is a decrease in the vapor pressure here. So this decrease in the vapor pressure of the solvent depends on the quantity of the solute present inside the solution. If we are using 10 gram of solute, then the vapor pressure depends on that 10 gram. If we are using 50 gram, in that case it will differ. Okay, so the solvent vapor pressure is dependent on the quantity of the non-volatile solute particles which we are adding. Now, for example, if 1 mole of urea is a non-volatile solute, okay. If I'm using 1 mole of urea or if I'm dissolving that in 1 kilogram of water, okay, exerting vapor pressure is same as that of 1 mole of sucrose. Sucrose is another solute dissolved in 1 kilogram of water at the same temperature. Okay, so here the mass of solvent is same and the solute amount quantity is also same. Okay, urea is also taken as 1 mole and sucrose is also taken as 1 mole. So the vapor pressure is also same for both of them. Okay, now according to Raoult's law is in general for any solution, the partial vapor pressure is directly proportional to mole fraction, right? That is, the Pi is directly proportional to Xa and the Pi. This is what we have discussed now. This is what we have discussed now. Now, this P1 naught, which is a proportionality constant, that is equal to the vapor pressure of the pure solvent. And P2 naught is the vapor pressure of the solute. And if we are giving a graph, we are getting a straight line. The same thing only is followed here also. Okay. So the vapor pressure of the pure solvent is taken as a straight line. And with this, I am closing the today's session. Okay. So what we have discussed. So the solid and liquid case is very, very less. Okay. In solid and liquid case, only very few theory part is included. Okay, that is the solvent vapor pressure will get decreased in the solution. That's all. Now in liquid and liquid only we have studied about the Raoult's law. So in which those three formulas are very important. Those P total is equal to P1 naught into X1 plus P2 naught into X2. So this is one of the very important relation. And also one more relation we have used, that Y is equal to Mx plus C format relation. That is again important, which is equal to P1 naught plus P2 naught minus P1 naught into X2. So this is the next important relation we have to use. And the sum of the partial pressure will be equal to the total pressure. So this is the third formula. And if separately, if you are getting questions from Raoult's law, you have to go with P1 is equal to P1 naught into X1 or P2 is equal to P2 naught into X2. So simply in general, if I have to write Pi is equal to Pi naught into Xi. Okay. So these are the four formulas you are learning from today's session. Got it? And at last week, the vapor pressure of the solution vapor pressure is always less than the solvent vapor pressure. Okay. So this is the next concept. So these are the 5 points you are getting from today's session. Okay. And you should know how to apply these formulas in the questions. I mean in the numericals. Is it okay? So do any of you have any doubts from the four formulas and from one theory part that we have discussed today? Students? Yeah, no. Okay. So here the fourth topic of this lesson is also getting over. The first is concentration, classification, concentration, Henry's law, and today we are completing with Raoult's law. So in tomorrow's class, tomorrow is a holiday, and on Monday, Sunday we will discuss about ideal and non-ideal solution. Okay. So what you all have to do is go home and solve as much of numericals as possible. Okay, solve more number of problems from the topics, 4 topics that we have discussed. Okay, you can get the questions from your NCRT book or from your modules, from anything. Okay, so we will also solve questions in the class after completing ideal gases and some, if I move on to colligative property, after completing few colligative property topics also, I will also discuss problems, but the problems which we are discussing here in the class itself is not enough. Alone is not enough. So you also have to give a try from your side. Okay. So here let me wrap it up the today's session. So meet you all in the next session. So thank you so much for listening the lecture today. Take care, students. Bye bye.